paper I'm presenting is called Constant Video Depth Estimation, which focuses on an algorithm that reconstructs dense, geometrically consistent depths for all pixels in monocular video. The reconstruction systems for video have much more difficult problems, such as jitter, motion blur, and the existence of dynamic objects. For these reasons, previous methods often lead to errors such as missing regions in depth map, inconsistent geometry, and depth flagging. Therefore, this thesis proposes a new video-based reconstruction system that combines the advantages of both traditional and linear-based. The method takes monocular video as input, estimates the camera pose, as well as a dense, geometrically consistent depth map for each video frame. When traditional reconstruction method failed, they typically return a whole or a very noisy depth. However, in other regions where there is enough confidence in the results returned, it is usually quite accurate and consistent, since they heavily rely on geometric constraints. According to this, combined with a linear-based approach, they have complementary properties. The methodology of the paper was carried out in 2 stages: pre-processing and test time training. For pre-processing, the thesis used the software CoMap to estimate the frames, in-camera parameters, out-of-camera parameters, and the semi-dense depth maps for N-video frames. For dynamic objects, they often lead to reconstruction errors. Applying a mask RCN to them in each frame to segment them out independently and suppress feature extraction in these regions. This is a traditional structure from motion approach, then combined with a linear-based reconstruction method. The next step is frame sampling, where the thesis computes dense optical flow for a given frame pair and theoretically obtains the concatenation of all levels of frame pairs. Finally, the optical flow is estimated, and for all frame pairs obtained in the previous step, they are analyzed using homograph web. This method is used to estimate motion between 2 frames. In arriving at the final result, the team found that the optical flow estimation results were not reliable for a pair of frames with very little overlap. So all pairs of frames smaller than 20% of the image area were dropped off. These are some examples of realization. For test time training, they first describe the geometric loss and then optimization of the whole in a given frame pair. The optical flow field describes which pixel pairs represent the same field points. These streams can be used to test the geometric consistency of the current depth estimate. The team believes that it is possible to turn this stream into geometric losses that backpropagate any consistent differences through the network, so that they produce a more consistent depth than before. Geometric loss consists 2 of the losses, one for differences in image space, and one for parallax. To do this team defines 2 losses equations, and these 2 equations analyze each other for relative coefficients. Geometric loss is the combination of these 2 loss equations. The network was fine-tuned with the ADAM optimizer for 20 epochs. The training will take 40 minutes on 244 frames of video. The final results were quantitatively compared with the most advanced depth estimation method, and then extension ablation experiments. These are some examples of realization. For comparison with the other state-of-the-art depth estimation method, although this paper has achieved good results, there are still some limitations. For example, larger camera movements produce errors that can have strong degrading effects on their results. Online processing video is not supported, and the training time is too long.